So if you take a look at activity number 3, it'll give you, I believe, this description. Tells you about linear regression, tells you about using Excel. So you should kind of read that and then walk through this example so you see that. See all these statistical analysis here? Well, that shows you the longhand way by which Excel does linear regression. You guys don't have to learn that, but know that there is a, back in the days when I was certainly in college, we had to do it this way. We needed to multiply two sums and then take the summation of it. Anyway, let me go ahead and talk to you about this activity. Read this especially, a spreadsheet for least square, because that talks you through Excel and how to use Excel to do least square analysis. Okay, so that's really the important part of this whole thing. And then remember this right here, where it says, in order to do Linus, we need to do Control-Shift-Return for PC. I think you also do that with a PC, Control-Shift-Return. So I'll show you how that's done shortly here. So let me go ahead and do the activity. This, by the way, is the tutorial on how to do Linus. So if you need to see, if you need a slow motion on how to do that, just click on this link and it'll show you again how to do it. But for now, I want to go ahead and do this for you. In the worksheet, show you the worksheet. This is what you guys are going to answer. It's basically what, 5 or 6 questions, but it requires you guys to use the spreadsheet program. So the first thing that you guys will do is put this in a data set. This is the methane and this is the signal in millivolts. So we're looking at the conductivity of methane, a methane solution, and this is the conductivity that we have. So this is what I did right here. I have the methane signal, that's 0.62. Let me just show you that. 0.62.122. So even though this is in a row, you need to put this in a column. That's the best way to manipulate data when you're doing a linear regression. And then the signals 9.1, 47.5, 95.6. So that's what I did. The next thing I'm going to do is I'm going to subtract right here. You can see it in this column I'm hiding. I'm going to subtract the blank from the signal. So the blank is when you have 0 methane, but yet when you have 0 methane, there's a background noise of 9.1. Okay, so I have to subtract 9.1 from all of these. So this is what I'm going to do. I'm going to clear this and then I'm going to show you how that's done. So let me clear this. And again, for those of you who already know how to use Excel, more power to you, because this should be a review. Okay. So what we're going to do here is we're going to take this signal and correct that signal. So I'm going to say, I'm going to press equals, and you can see what I'm typing up here in the toolbar or the formula bar. So I'm typing in equals. Whenever you have an equal sign, it means it's expecting a formula. If you don't have an equals, it's not expecting a formula. So I'm going to say equals, and then I'm going to click right here. Okay, C, and this happens to be cell C4. How do you know it's cell C4? It's in column C, and it's in row 4. That's why if I click here, it puts C4 right there. Okay, and then I'm going to subtract C4 from C4, because C4 is the signal for 0. And then I'm going to hit return. Okay, and it basically, if I click on that cell, you can see the formula, C4 minus C4. So when I have 0 methane, CH4, I should have 0 signal. Now the key to Excel is that it does propagation of calculation, which means that if you have one equation and you program Excel correctly, then it can do that same equations over and over again. You don't have to keep typing it in your calculator. And the way you do that is click on this block and then move your cursor right to this bottom right arrow. Okay, let me blow that up so that you guys can see. Okay, I'm taking my cursor and I'm moving it to the bottom right corner so that I see the plus. Once I have that plus, I'm going to press down on my mouse and then drag it down. And when I'm pressing down and dragging it down, it's going to repeat that same calculation on that cell for the other cells right here. So this one is C4 minus C4. This one C5 minus C5. This one C6 minus C6. And so that's what it does. It does a propagation of calculation. The problem with that right there is that I'm subtracting the signal from itself. I need to subtract the signal from C4, not C5 from C5, but C5 from C4. So the way I do that is I go back to my original, and if I put a $ right before the C and another $ right after the C, it tells Excel that I'm going to keep that cell constant. I don't want a relative calculation. Relative means that if I'm moving down a row, everything moves down the row as well. If I go across the row, everything goes across the row as well when it does the propagation of calculation. What I'm telling Excel here is that I'm going to take C4, but I'm subtracting C4, and when I do a propagation of calculation, it will always be C4. So now that I do this, that's still 0. Then I'm going to click here, and then I'm going to hold this and then drag it down. And now what you see is that each cell has 9.1 subtracted from it. That's the magic of propagation of calculation that Excel. That's why we love Excel when we do science, because you're basically just going to repeat a bunch of calculations when you do an experiment, and the calculations will be similar if you do the right analysis. So why keep punching it into your calculator and keep you could have calculation punching error? Just let Excel do the propagation of calculation for you. So that's basically it. Okay, that's the corrected signal. The next thing we're going to do is we're going to plot this. Okay, so look at I'm going to make this smaller. Look at the directions right here. And it says right here, subtract the blank from all other values, then use Linus to find the slope and intercept of this uncertainty, plot the data for this question with the linear equation expressed. I'm going to do B, and then I'm going to go back to Linus. Okay, so just bear with me. So I'm going to plot this first. And the way I plot is I have to highlight this row. And then I also need to, that's my Y values. Then I also need to highlight my X values. But you can see that if I highlight this, and then I go over here and highlight that, then it forgets my original. What I need to do is highlight this, and then I don't know what it is in the PC, but in the Mac, I hit my Option key down. Sorry, I hit my Command key down, and the Command key is the one that looks like a it looks like a hashtag almost, except it's got loops at the end. Okay, but I need to highlight these two columns because those are the data that I'm going to collect. Then I go up here and insert a chart. It's nothing more than a graph, and I'm going to do a scattered. I'm going to do a scattered. When I do the scattered, it should automatically generate that graph for me. And you can see it does. Okay. Again, let me walk you through that. You have to highlight your X and your Y values. These are my Y's. Then I'm gonna hit Command and highlight my X. If I just highlight these like that, then this signal, Excel won't know what to do with the middle. It's gonna get confused. I gotta highlight my Y's and my X. by pressing Command while I highlight X. And then now that it's highlighted, Excel knows what the data sets are. In fact, what I need to do is I could highlight the heading here and here. That way I have labels for my graph. Let me do that again. And then go to chart, and you're going to insert a chart, and it's going to be an XY. So that's what you have right here. Okay. Next thing we're going to do is we can change this. If we click on this right here, we can change the title. This is just the signal versus methane. So I can just go in here and put in signal versus methane. So I can, in fact, that's what you guys will need to learn how to do, is properly label your graph. Right here, I'm going to label this. If I click on this chart, you see that there are little ghost boxes here. I can take that and make it smaller or drag it around, okay, and change what it looks like. So the reason why I did that was because I need some space on the edge here so that I can put a label. And if I just do, let's see, I think I can insert. If I go to home, and then I'm going to insert a box here. Yeah, right here. Then I'm just going to type in, this is methane. And according to my graph, that's the methane signal. And this happens to be in volume percent. So don't forget to do that. Take this and hold your Option key down so you can duplicate it. Make that at a 90 degrees. Bring it over here. And then what I'm going to do is I'm going to click here. And I'm going to say that is corrected signal. Signal corrected. And when it does that, I just need to make this box bigger. So you need to practice that because, again, this is the training ground for when you guys start using Excel in your data analysis. The next thing I'm going to do is I'm going to take my mouse and just click in any one of these data points. I can click here, I can click there. I'm just going to click that. And then I'm going to hit my Control or right click if you're a PC. And then I'm going to find this contextual menu. And I'm going to add something called a trend line. Add trend line. A trend line allows you to do the linear regression. I can do exponential regression, logarithmic regression, polynomial. I'm doing linear regression right here. And I'm also going to, I'm not going to set the intercept to 0, but I am going to show the equation of the line. This is the equation of that line. And I'm going to do the correlation factor R squared. R squared tells you the goodness of fit. If R was a perfect 1, it means that the line fits right on top of those data points. Right now I have 3 nines, and that's pretty good. You usually quote the correlation, how good the data fits the line based on nines. 3 nines is really good. If you have only 1 9, that's okay, but it's not that good. If you don't have any nines, then the correlation's even worse. So this is the equation right here. I'm going to just click on that, and then whenever you see this arrow like that, it means it's a handle and you can drag this around, okay? If I click here and I don't see that, I can't really drag it. I need to go to the edge, and then your mouse will convert to that, and then you'll see. I can also stretch this by moving this here. Sorry. okay, by clicking on that handle, and then I can make it bigger or smaller, but you need not worry about that here. I'm just going to move this to a clean spot. Now we're going to do Linus, because right now we've already completed this plot, the data for this question with the linear equation expression inserted. This right here is the linear equation expression inserted. Now I'm going to do Linus. Linus is a way of getting these data points. Y equals mx plus b. So m, slope is 869.13. B, the intercept is 22.085. What I need to do in order to get Linus to work correctly is highlight a 2x3 areas. And if you look in your lab manual, this part right here is your slope. So I'm going to highlight this, and I'm going to basically box it in, okay, like this. And so this area right here, that's your slope. I'm going to justify it to the right. This one right here is your, and this is found in your lab manual, okay, where it says a spreadsheet for least square. And if you look in that, you will see that this right here is S sub m. S is your error for m. It's a standard deviation for m. And this right here is your correlation factor, r squared. And then on this side, these three is going to represent b, that's your intercept. And then the next one is the S sub b, which is your standard deviation for the intercept. And then finally, S sub y. Sure I got that right. Yeah, S sub y, which is your standard deviation for your y-axis. I do that just as a label. Okay, I do that just as a label. Next thing I'm going to do is I'm going to highlight these 2x3. Then I'm going to go to the equation bar. So what you need to do first is highlight these, okay? And then you need to go to the equation bar so that you can put in the equation that you need. Once I'm in the equation part, I'm going to put in equals, because it's an equation, Linus, and then I'm going to do left parentheses. Right away, it tells me I need my known y's. My known y's are these, so I'm just going to highlight these. And then I'm going to put a comma, and then my known x. So I'm just going to highlight these. I don't have to press command for this. It's waiting for the known x. Then, comma, true, comma, true. Right parentheses. Don't hit return yet, though. Okay, that's very critical. You do not hit return. Then put your cursor at the very end. Make sure that that 2x3 is still highlighted. Put your cursor in the end, and then if you look on your lab manual, it says you need to press Shift, Control. So hold that down, and then return. If you do not do that, you're going to get an error. So you need to hit Shift, Control, Return. When I do that, all the data that I want, the intercept, the slope, the correlation factor, the standard deviation for the intercept, standard deviation for the slope, they're all filled in. Again, the magic of Linus. Now let's make sure that this number's right. Remember this, I told you this is a slope. Look, 69.13, 69.1349. Slope's correct. This is the intercept, negative 22.08, negative 22.085. Okay, so it's here. Don't worry about the standard deviation. It just kind of tells you how well the data fits. Look at the correlation factor, 0.99251, 0.993. So it rounded off the 251 to 3. So that's how you would do this. Okay, again, not so much that you get this right, but you need to learn how to use Excel. So when we go over here and we look at this graph, make sure there are no questions. Okay, some of you are saying that in PC you do control return. Yeah, that's correct. In the newer Mac, if you have newer Mac or newer Excel, it's actually the Excel version. You might have to do. You could also do Control Return. The Excel that I have, I think, is like 2014. So I still need to do Shift Control Return. That's a problem with Microsoft sometimes, is that they change the command sequence on you, and so you have to be updated. So older Macs or older Excel, Shift Control Return. Newer Excel, it's just Control Return. You just have to play around with it. Anyway, we're done with this question. Okay, we're done with this question. You need to print this out and then submit it with your worksheet. Okay, just put it in a separate sheet of paper. You can do a screen capture, or you can print it out and then or put it in a PDF file. Let's take a look at the second question. The second question is, what mass of iron? It's diammonium, NH4, disulfate, iron. I believe that is an iron. Let me see. Sulfate's -2. That's an iron 4. No, ammonia's +2. Sulfate's -2. So that's an iron 2. The oxidation state of that iron is +2. What mass of the iron compound is required to prepare 500 milliliter solution containing 100 ppm of iron? So that's a little bit tricky. You guys need to use dimensional analysis. I'll help you get started, but you need to do that calculation. So let me shift gears here and let me show you my iPad so that you guys can see this. Hopefully it'll be there. So bear with me a bit while I prepare a surface for me to write on. And let's see if I can share that screen with you guys. Why is it not working? Oh, I know why it's not working. Hold on. I need to, I only have 2 ports on this Mac. And so the problem is that when I put in my external hard drive, because I'm doing a second monitor, it's not allowing me to hook up my, iPad. So I gotta make sure the connection's there. Okay, the connection's there. Go ahead and do that. Okay, so let me go ahead and help you with this. I'm going to help you set it up. You have to do the calculation. Okay, so this chemical has sulfate, iron, ammonium. You need the molar mass of this. Okay, you need to calculate the molar mass. So let me go ahead and I won't calculate the molar mass for you, but I will show you how to set this problem up. So let me share my screen so that you guys can see that. Okay, at this point you should be able to see my iPad as well as my monitor. Okay, there was a question here. Can you show how you did the MSM R squared value on the chart, not the graph? Let me go back. What you need to do is, let me delete this. Okay, the graph is separate. I don't even need the graph to do Linus. This is a Linus command. What I did here is I just labeled the outer portion of these data set, so I know which is the slope, which is like this would be the slope right here. This right here would be the intercept. Okay, this right here would be the standard deviation of the slope. This right here would be the standard deviation of the intercept. Okay, this would be the correlation factor, and this would be the standard deviation to y. So it's sort of color coded so that you can see how the label corresponds to this 2x3 box.
So
what I need to do
amount of data. Sorry.
Yes.
So up? Given amount of data, would Linus provide you with those 6 sets of information?
Yes, that's what Linus does. Okay, that's what Linus does. It gives you that. No other program will do that for you. Linus does that for you. It gives you better statistics. And again, let me just highlight, you have to highlight that 2x3 first, and then you move your cursor to the equation editor and type in equals Linus, left parentheses. It's going to prompt you. You can see right here, it's prompting you for the y values. So you just have to highlight that. You have to highlight it by clicking and dragging down, comma, the x values, clicking and then dragging it down, comma, true, comma, true. True and true just tells you the conditions by which this program is going to operate. Then once I have that, I'm not hitting return. Now I'm doing either control return, depending on the version that you have. My version is control shift return, and then it generates that value for you. So that's again what Linus does. You guys will be doing it a lot this semester. So dog ear that particular page in your lab manual, or put it down somewhere, because you guys are going to be doing Linus. In fact, in this activity, you're going to be doing Linus again. So hopefully that's clear. Okay, if you have any other questions, let me know. Do you just input it as SM? Yeah, you just type in SM and R squared right here, but Linus generates the value for you. Okay, Linus generates 10.64 and 0.999251, but these are just labels. These are just labels right here. So let's go back to this problem right here, because you guys are going to have to do a little bit of math. So it says in this question, what mass of, so we have this iron compound, Fe, Fe, let me change this. Keep getting this message from my daughter who just moved to New York. Fe, NH4, 2, SO4, 2, and then this compound has a bunch of water, so make sure you include that in the stew water. So the 2 water is going to be, I don't know how to, 2 waters right there. Okay. Oh, man. Sorry about that. I gotta turn off my messenger on this iPad. I don't know how to do that. So you're just gonna have to read the iMessage from my daughter and my wife. Anyway, the question here, let's go back to this page. It says, what mass of diammonium sulfate iron 2 dihydrate is required to prepare 500 mils? So we have 500 mils. Solution. This is solution that contains 100 ppm of iron. So not of this chemical, but just of iron. That means you need the atomic weight of iron, and you need the molar mass of this guy, because you need to know what % of iron is in this guy. Okay, so we can easily do that based on their molar mass. Let's just say that this, there's 18 twice, let's see, 18 twice, iron's about 55, sulfate's 96, water's about 18 um, times 2. So this is an approximate molar mass. It's not an exact molar mass. You guys are going to have to do that. That's 100. That's about 36, 236, 55. So, and 36. So that's 12, 17, 6, 7, 12, 327 approximately. Okay, so let's say that the molar mass for this guy is approximately 327.
Professor, oh, the page that you pulled up of activity 3A is blocking that, the where you're writing. Can you remove? Yeah. Thank you.
Not a problem. Thanks for. So let's say that this is approximately 327. We need 500 milliliters of this solution. But that solution needs to contain 100 ppm of iron. Okay, so the way you want to tackle this is, the question is what mass of iron? So we need to know the mass of this guy. That's why we need the molar mass. Let's say that iron has a molar mass of about 55. Let me just double check, make sure that that's correct. Yeah, 55.847. I'm just going to approximate it to 55. You guys got to do the exact number. This is just kind of showing you the ropes. So what we need to do is we need to figure out exactly what mass of this guy contains 100 ppm of iron in 500 milliliter solution. One ppm, by the way, is 1 parts per million, or 1 milligram per 1 liter of solution. That's 1 ppm. And we're going to use that to our advantage. Okay? So the first thing that we need to do is we need to use, in this particular case, this quantity, 100 ppm, 100 milligrams of iron, because that's what we're after in 1 liter. That's 100 ppm. And that's iron, not iron diammonium disulfate dihydrate. We're going to convert milligrams to grams. You know, there's 1,000 milligrams in 1 gram. Then we're going to convert grams of iron. 1 gram. Sorry, it's not 1 gram. It's 55 grams per mole of iron. And this, we said, was 327 grams per mole of Fe NH4 2SO4 2 waters. See, the moles cancel. Now you've converted your mass of iron to mass of compound using dimensional analysis. That's the magic of dimensional analysis. That's why you can never forget how to use dimensional analysis. When you cancel all of these, what you get is grams per liter of this compound. Now, what you need is grams. And what you have that I didn't show you is that you have to prepare 500 mils. So your next step is to convert liters to milliliters, and then multiply by 500 mils. And that'll be the mass of that compound that you need in 500 milliliters of that solution that will contain 100 ppm of iron. The magic of dimensional analysis is that I didn't have any clue how to solve this problem. I just let the units develop the equation for me. Okay? I let the units develop the equation for me. So that's how you would handle question 2A. You use dimensional analysis.
Question.
2B,
Oh,
yes,
question. I just was wondering, for the 100 of the iron, how did you get that number?
100 ppm, or
Uh-huh.
this right here, because the question, if you read the question right here,
Oh, yeah, I couldn't see the whole
that's
question.
100
Okay.
ppm, so that
All right.
means it's 100 milligram in 1 liter.
Okay,
Because
so
1
so the question.
is 1 milligram. So remember this, write it in your lab notebook as well. 1 ppm is 1 milligram of anything in 1 liter. Okay. So yeah, good question, because that is easily forgotten. Question B, I'm going to switch. Question B here, 2B, it says I'm going to use the stock solution. So the stock solution is 100 ppm of iron. That's my stock solution. Okay, it's already defined in question 2A. What aliquot must be used to prepare? Aliquot is what volume is used to prepare calibration solutions. So my calibration solutions are all going to be 100 milliliters volume, and it's going to have concentrations of 0.100 ppm, 2.0 ppm, 4.0 ppm, and 7.0 ppm. Whenever you see this, what should come to mind to you right away is dilution. What we're doing is we're diluting 100 ppm to zero point 0.1, 0.5, 2, 4, and 7. So that's a C1 V1 equals C2 V2 problem. Your C1 is 100 ppm. Your C2 are these. So you have to do 4 calculations. Your V2,
We can't see it.
oh, sorry. These are your C2s. Okay, you have to do 4 calculations. Your V2s are all 100 mils. So you need to figure out how much of that 100 milliliters do you need to put in 100 milliliters and fill to the mark so that you have zero point 0.1 ppm iron. In another solution, you need to figure out the volume of this 100 ppm and fill to the mark with water, so you have 2 ppm. So you're trying to figure out what portions I'm going to put in each one of these vials so that I can prepare these solutions. And one of these will be 0.1, 0.2, or 2, sorry, 2.0, 4.0, 7.0. So the stock solution is going to be 100 ppm. So how much do you have to fill that and then fill the rest with water? How much do you have to fill that? How much do you have to fill that? How much do you have to fill that? And then the difference will be the water to give you a total volume of 100 milliliters. And it's C1V1 equals C2V2. That calculation is pretty, hopefully, straightforward. Once you have that, then that's where you put these right here. Okay, you put each one of those concentrations right here in this line, and then you generate another graph, and that graph is going to be volume versus absorbance. So I think I might have that somewhere here. Let's see. No. Okay, let me just sort of generate that for you. Okay, so what you need to do is, let me put out my Excel spreadsheet here. Sorry. And according to this, I'm going to have volume and absorbance. So I'm going to just label this 1, oops, what, 1, 2, 3, 4, 5, 6, 7. Okay, and this will be the volume, and this will be the absorbance. And the absorbance in this particular case, let me load this up. It's going to be shown on the graph or the data set. So that's going to be 0.0122 for the first one. Second one will be 0.0608. Third one's 0.2322. Last one's, the next one's 0.455. The last one is 0.5858. Okay, I don't have a 6 and I don't have a 7. So you guys are going to take this and you're going to fill in the volumes that you calculate from question 2B. Okay, from question 2B, and then you're going to fill it here, and then you're going to generate another graph. And then you're going to use that, because that's your calibration graph, to answer this next question right here. This next question is, construct a calibration curve on the data above using Linus to find the slope and intercept and their uncertainties. Okay, so you're using Linus in this as well, just like we did in 1A. Are there outliers in the data? Outliers simply means this. Let's go back to this right here. Yeah, this. Let's take a look at this graph, because I want to show you what we mean by outliers. Outliers just means that the data doesn't fit. So I'm going to generate a graph again, because it looks like it got lost. I'm going to highlight this. I'm going to highlight this. I'm going to generate that graph again. By the way, when you highlight these X and Y, you have to go in the correct order. You have to highlight the X first, and then you need to highlight the Y first. Otherwise, it's going to switch your slope on you. Oh, that's the reason why it wasn't working. I already have a graph right here. I couldn't see it. So I'll bring it up. Now, what I mean by outliers is that you can see how these things are all pretty much in a straight line. Suppose one of these, I'm going to force one of these, let's say that I force this one to be some weird value. I'm going to change this to equal 0.478. Okay, you can see right away that it breaks away from that line. It's outside. In fact, I'll make that more pronounced. I'll make this 7, 8. So you can see that it really messes up the graph. So that's an outlier. Okay, it basically is an anomaly outside the main. If you can eliminate that, then your correlation factor, because look what happened to the correlation factor when I introduced that error. It went from 9 3s to only 3 9s to only 1 9. So what happened? Well, it's a bad correlation. So what we can do is I can just take that whole row and delete it. So what I'm going to do is I'm just going to delete that. I'm going to just clear that data set. And when I delete that, then it doesn't take that into consideration when it's doing the linear regression. And look what happens to my correlation factor again. It goes back to 3 9s. In fact, it's a 9995. So that's what we mean by outlier. So in this question right here, you're going to have to take a look at your graph that you generate here and see whether or not there are outliers. May be a data that was incorrectly written down, or maybe there was just an anomaly on that particular sample. Remove it and do the correlation factor again and see if you can improve it. So that's what this question is asking. Yes.
It'll come up later in experiments, but whenever we do work, do we have the, not, I guess, prerogative? Are we able to just remove
Remove
outliers
the
whenever
data?
we feel like it?
Yes and no. Uh, what there is, you guys don't know this yet, but there's something called a Q-test, and the Q-test tells you whether or not it's reasonable to remove it. Okay. When that time comes, I'll show you that. But you never want to just eliminate data just because your data looks better without it. There's got to be a threshold by which you keep it, because you work so hard to generate that data. You just don't want to just freely throw it away.
Right.
But if it improves the overall results and it doesn't take away, then yeah, you can do that. Okay. But you have to justify
It'll be
put it
pretty
right.
obvious, I assume, just
Yeah, right.
whether or
Right.
not we're
But justify it, say this is what it was after removing it, because maybe I saw that that solution was a different color. So I already know ahead of time there's going to be an anomaly there. Then it's certainly very justifiable. Okay.
Okay. Thank you, Professor.
No problem. So that's what this part is. You're going to, I can tell you right away that right now you're going to have to throw away one of the data points to get a better correlation factor. Okay. Once you do that, then the last part is to take that better graph that has a better correlation factor, find the absorbance, find the absorbance in which a blood contains 0.335 iron. Determine how much blood should be diluted in 250 ml vol flask. The appropriate solvent to be given an absorbance of 0.250. So what we need to do is we need to work backwards. We use the graph, and you can see that 0.250 is between the third and the fourth points. What you need to do is you need to figure out, let me blow that up a little bit. Okay. You need to figure out what concentration, what volume gives you 0.250 exactly, because that's the data point that you guys are going to be using for this calculation. Okay. You're using the graph that you generate in 2C in order to work out 2D. You're going to find that volume or that concentration of iron, that gives an absorbance of 0.250. That's what this particular data set gives. And it's going to be between the fourth and the fifth. It's going to be between 4 ppm and 7 ppm. You have to figure out the exact value. Once you figure that out using the graph, then you can use that exact number to solve this last problem. You're going to know that that's how many iron per liter, that milligrams of iron per liter. And you're going to have to back calculate. Remember that we're going to use a 250 ml volumetric flask, and we're going to figure out how much blood to use so that it has 0.335% iron. I'm not going to do much more than have you guys figure this problem out using dimensional analysis. This thing's not due till Friday. If you have questions on Wednesday, then we can go over it. Okay? So
the activity is due Friday?
This thing's due Friday. It says tonight. I changed it to Friday.
Oh, okay. Yeah, I was stressing out about that. Thank you.
No. It's good that you're stressed out. That means that you've completed a lot of it already. So, but you guys have till Friday to do that. Remember that whenever we start work on Monday, especially an activity, it won't be due till Friday. If we start an activity on Wednesday and finish it on Wednesday, it's not due till Sunday. So that's my general philosophy in terms of this shelter-in-place deadlines. You guys have a few more days since we're not actually going to be in lab. I mean, I can have you in Zoom for 3.5 hours, but you guys don't want to do that. I don't want to do that either. So I'll let you guys work at your own pace. You guys, are you guys okay working alone, or you have questions? I can put you in rooms so that you guys can like at least tackle the first problem.
Sophia had a question.
Yes.
She wrote it in chat.
Oh, sorry. Let me take a look in chat. Let's see. Yeah, there's a bunch here. Let's see. You can't do Linus in Google Sheets, exactly. Sorry about that. Oh, it does? If if you guys know how to use Linus in Google Sheet, show us a remedy. That would make it easier for everyone. Or at least, I guess you can Google it in Google Sheet if you can do Linus. Okay? Um, yeah, the Zoom recording should be available. It usually takes me a few days, but I'll try and get this out to you by Wednesday. I'll make a special effort for that. Um, yeah, you guys can have a group chat. You guys can communicate. Just make sure that when you turn in your work, it's your own work. So I don't know how you guys do your group chat. You guys are millennium. You guys can figure it out. I don't know how to do that. But if there's any other questions, fire me an email or we can discuss this on Wednesday since it's not due Friday. Any pressing questions here? And then if you guys, yeah, if you can do Linus in Google Sheets, wow, that's pretty good because I know that we couldn't do it like a couple years ago. Maybe they've changed it. Maybe they realize it's really important. So if not, yes, what's the question? Okay, any questions? I have a question. Yes, Daniel. Is it to everyone or is it just to? For 2B, do we use 100 ppm for all the C1s? Let me take a look. Yes, because that's your stock. Stock solutions are like the original part. You're always using that original solution to prepare the others because if you use subsequent solution, any mistakes will be propagated. So whenever you do a dilution, you always want to prepare the first one really carefully because if you make a mistake on that first one, everything else gets ruined. Okay, so you're using the 100 ppm to do the calculations for the rest. Okay, the ppms we are given is the milliliters we need to calculate. Yeah, the ppms that you're given, well, you'll see that I've made this problem really easy for you. As it turns out, the milliliters is equal to the ppms. Okay, it just turns out that way because I made this problem easy that way when you do the calculation.
Excuse me, Professor, I have a question as well.
Sure.
So when we were talking about the serial dilution in the past, it was molality or M1V1 equals to M2V2. And now we can just generalize if concentration is in any form like this one, we can just use that formula as long as it is like constant with all of them or consistent with all the.
Yeah, that's exactly right. When they gave you M1V1 equals M2V2, they showed you that the moles of before dilution is equal to the moles after dilution. What they didn't show you, and I wish they did, was that that equation is true for any concentration, whether you're talking about molality or mole fraction, because the units will cancel out. Okay, you do dimensional analysis, the units cancel out, so you can do that for any type of concentration variation. So yes, that's what you could do in this particular case. But it is an extension from M1V1 equals M2V2. We're just generalizing it.